Today, we're diving into an exhilarating field of physics that could change the way we think about energy forever. Let's talk about quantum engines, a groundbreaking concept powered by nothing less than quantum entanglement. Quantum entanglement sounds like something straight out of a sci-fi movie, doesn't it? It's a phenomenon where two particles, no matter how far apart they are in the universe, remain connected, communicating in ways that defy the conventional laws of physics. Recently, researchers at the Chinese Academy of Sciences have taken this baffling concept and turned it into a fuel for quantum engines. Now, unlike the engines in our cars which burn fuel, or even the electric engines that use batteries, a quantum engine operates on a completely different level. These engines utilize lasers to manipulate particles between different quantum states, effectively converting light directly into kinetic energy. Imagine an engine that's not bound by the usual rules of thermodynamics and can theoretically achieve efficiency levels above 25%. In their experiment, the scientists used ultra-cold ions trapped in a magnetic field and manipulated these ions using lasers. The frequency, amplitude, and duration of these lasers were finely tuned to transition the ions from their normal states to entangled states. Over 10,000 trials demonstrated that as the ions became more entangled, the engine's mechanical efficiency increased, although the overall energy conversion efficiency remained stable. This is not just about powering quantum computers or futuristic circuits. It's about redefining what's possible in energy conversion and efficiency. Now that we've explored the fascinating concept of quantum engines powered by entanglement, let's delve deeper into one of the critical components of this groundbreaking technology. Ion traps are extraordinary devices that use electromagnetic fields to confine charged atoms or ions in a small region of space. These devices are pivotal in experiments involving trapped ions, such as the quantum engine we discussed earlier. So, what exactly are ion traps? They are designed to provide excellent isolation of the trapped ions from the external environment, while allowing precise manipulation of their internal states. This makes them perfect for delicate quantum experiments. There are various architectures for ion traps, including pole traps, which use radio frequency and static electric fields, and penning traps, which combine static electric and magnetic fields. Ion traps have a wide range of applications, from quantum simulation and computing to networking, time standards, and fundamental studies in quantum dynamics. In the realm of quantum computing, qubits, quantum bits, are stored in the stable electronic states of each ion. The collective quantized motion of these ions in the trap allows for the processing and transfer of quantum information through interactions via the Coulomb force. One of the key advantages of trapped ion systems is their scalability. Researchers have demonstrated fundamental quantum operations with high accuracy, and shuttling ions in an array of ion traps allows for scalability to arbitrarily large numbers of qubits. This makes them a promising candidate for future quantum computing systems. In the quantum engine experiment we mentioned earlier, ultra-cold 40K plus ions were confined within an ion trap. Researchers precisely adjusted laser parameters to manipulate the ion's internal states, transitioning them from pure states to highly entangled states. The stability provided by the ion trap allowed for a controlled environment to study the entanglement-based quantum engines. Understanding ion traps is crucial for grasping the full potential of quantum technologies. These devices are not just tools, they are the foundation upon which future advancements in quantum mechanics and computing will be built. Now that we've explored the science behind ion traps, it's time to dive deeper into one of the fundamental forces that make these traps so effective: Coulomb force interactions. Coulomb interaction and trapped ions. A Coulomb crystal, also known as an ion Coulomb crystal, is a collection of trapped ions confined in a crystal-like structure at low temperatures. The equilibrium within these structures arises from the repulsive Coulomb interaction between ions, which competes with the electric and magnetic fields used to confine the ions. These trapped ions experience both the Coulomb force, due to their charges, and the ponderomotive force, due to the time-dependent fields in the trap. Collective motion and quantum computing. In trapped ion quantum computers, qubits are stored in stable electronic states of individual ions. The collective quantized motion of the ions, driven by their Coulomb interaction, plays a crucial role. When ions are laser-cooled and ordered into long chains, They exhibit collective modes of motion that allow information transfer and entanglement mediation. This collective behavior is essential for the functioning of quantum gates and the overall operation of the quantum computer. Melting and recrystallization. Occasionally, ions collide with residual background gas particles, transferring energy and disrupting the crystal structure. Such collisions can lead to melting, where the ions transition from a regular crystal to an ion cloud. Efficient recrystallization requires precise control of Doppler cooling parameters. This process ensures that the ions return to their ordered state, making the system ready for further quantum operations. Understanding the dynamics of Coulomb force interactions in trapped ions is vital for advancing quantum technology. We've journeyed through the science behind ion traps and Coulomb force interactions. But now let's explore a question that excites scientists and tech enthusiasts alike. How will quantum change our computers? Quantum computing holds immense promise and could significantly transform various aspects of our world, including the field of computing. Let's explore how it might impact our computers. Exponential speed-up. Quantum computers leverage the principles of quantum mechanics to perform calculations exponentially faster than classical computers. Complex problems that would take classical computers millennia to solve could be tackled in seconds or minutes by quantum computers. Applications across sectors. Healthcare. Quantum computing could accelerate drug discovery by simulating complex molecules, leading to faster vaccine development and personalized treatments. Finance. Quantum computers may enhance risk assessment, portfolio optimization, and credit calculations. Materials. Science. Quantum simulations could revolutionize material design and discovery. Climate modeling. Quantum computers might improve weather predictions and climate simulations. Challenges and risks. Security. Quantum computers pose a cybersecurity risk. They could break current encryption systems, potentially compromising sensitive data. Transition to post-quantum cryptography. Organizations need to prepare for the transition to encryption methods resistant to quantum attacks. Quantum supremacy. In 2019, Google's quantum computer solved a problem in minutes that would take classical supercomputers thousands of years. Achieving quantum supremacy demonstrates the potential of quantum computing. As we stand on the brink of this quantum revolution, the possibilities seem endless. From accelerating medical breakthroughs to revolutionizing financial systems and beyond, quantum computing promises to reshape our world in ways we are only beginning to understand.